Hey guys, let's take a look at today's lesson. So today's lesson we're going to be looking at accumulation and population density. So accumulation is basically, we've actually talked about that before. We covered that last semester. So this is a bit of a review for the accumulation part. Population density, though we did this most simple of the population densities last semester, the very first one, population on a segment, we really haven't gotten into it and explored all the different types that we might see. So that's what we're going to be doing today. Today's lesson does require a calculator. Hopefully you brought one with you. If you don't, we can deal with that when we get to daily work, but we will need a calculator for this. Alright, so density, that's kind of a physicsy thing. I'm sure y'all are, those of you that have had physics or in physics, maybe you've already talked about density, I don't know. But density is a measurement, and the units is typically, it's measured in mass per unit volume. That's usually how it's measured. In Cal 2, this is about as far into density as we get, are these types of problems. In multivariable calculus, we deal with density a bit more in multivariables. So let's look at the different types of density we'll encounter. The first type is population just on a segment, like a line segment, if you will. So we just have population on a straight line. That's this here, population on a segment. What would we do? We would take the density, which is typically going to be given to you as an equation, some kind of an equation that would generate density, and then we would multiply it by the length of the interval. In this particular case, like the length of the interval is delta x. That's our length. This is the type that we did last semester when we were doing measuring along a segment. So when we integrate density, we get number of people. So density, the density for a population would be like, you know, if we wanted to discover population density, say in, you know, Highland Park, University Park, we could count up all the people that there are, and we could divide by however many square miles or whatever it was we were doing, and that would tell us, you know, in general. But these equations, these density equations, are typically, they're written to where, you know, maybe there are more people in one part of the city than another part. The equation, the density equation that's written would take that into account. That's why we would need an equation for it. It would calculate for us the density in a particular place as well as overall. Alright, so that's population on a segment. Pretty straightforward. All we do is we integrate the density equation. That's it. The length of the interval is our delta x, which we learned from our fantastic scary Riemann sums. Delta x is dx. So we would just integrate density. We're good on population on a segment. We get a little bit more complex when we look at population, these two here, on a ring or on a strip of land. So this is where we still are going to have given a density equation that calculates the density in particular locations for us. But instead of multiplying by the length, which is just dx, delta x or dx, we actually have to multiply by the area of that space and then times the dx or dr. So if we're looking at a ring, let's think about this like a circle. Okay, so we have a circle. Let's say our population exists in a circular area. Okay, so this, you know, would be our radius. If I wanted to take one of these circles and open it up, you know, cut it open and open it up, it would look like this, right? With this length would be 2 pi r. That would be the length. If I were to take a strip of the circle, you know, cut it, open up, that's the circumference, right? And then this part would be delta r. So our formula isn't simply, you know, the integral of density dx. In this case, if we have a ring, if the population is on a ring or circular area, it's the density formula, whatever that happens to be, times the area. So here's our density formula. So our area is going to be our length times our width, right? Length would be the 2 pi r, and the width would be delta r, which is just dr. So this would be the formula. We would take our density function, multiply it by 2 pi r, and then times delta r, which is just dr. Okay, and that we would integrate that from the radius out. So if we're in a ring, you know, the variable that we have is an r. The radius starts at 0, right? We have 0 radius in the center of the circle, and then we go out to however much, however long the radius is. So that would be the formula for population on a ring. That's how we would do that. The last one is population on like a rectangular area, like a whole strip of rectangular area. In this case, we still have to multiply the density times the area, and the area in this case takes on length. So we'd have our density formula, which is p of x, or whatever variable we're using, and we multiply by the length. So let's say in this case, whatever the length is, 5. And then this would be our dx, just depending on which way we were going. So I have an example of each of those 3 types, so at least you can get a feel for how those are set up. And we also, of course, have an accumulation problem, which would be a review. All right. General questions before we start? Okay. So the types of problems that we will be encountering for the most part have to do with this population density. That's what we're going to be looking at. There are other density problems that we would encounter mostly in Cal 3, and that's density of actual substances like water or air, metal, wood, something like that. These are mostly Cal 3 problems. If we encounter them in Cal 2, you'll be given a density function and you'll be told, whether it's a strip or circular or rectangular. All right, so let's look at our first example. We have a city located along a straight highway. Straight highway tells us which kind we're doing. This is going to be a segment. It's a population on a segment. So we have a straight highway. And it can be approximated by this function. So here's my density function, where x is the distance from the town square. Here's the town square, measured in miles. So our point of focus is the town square. The town extends for 4 miles on either side of the town square. Because this is our focus, we would be going left, so that would be left, so -4, and right to 4. Our bounds are going to be -4 to 4 because of the orientation. We're measuring everything from the center of the town. If you decide to have your bounds 0 to 8, you're going to get a different answer unless our equation is symmetrical. So you really kind of need to pay attention to where we are focused on. What's our point of orientation? And in this particular case, it's the town square. That's our point of orientation. So we go left and right, so negative, positive. So let's write our integral. We're going to go from -4 to 4. This is the simplest kind. We did 1 or 2 like these last semester. We're going to take our density function, which is 1500 times 4 minus x, and just multiply it by dx, or delta x, which is just dx. I mean, that's all it is. Then we would enter it into our calculator. This is a calculator lesson. Now we are dealing with people, so if we get a fractional number, I hope we are comfortable and know what to do when we're dealing with like live things, like people, animals. We don't round up. If the density was, I don't know, 5,000 people in an eighth, we don't actually count the eighth of a person, right? We would just count 5,000. We would just truncate. We wouldn't round. So when we work this out, it's actually 48,000 people. That's how many people are in this particular town. Okay, so this is the simplest one. This is one on a segment. And do we see how we know it's a segment? It's because it says straight highway and it's not talking about a width or anything. It's not talking about that. So that tells us it's on a segment. Okay? All right, let's go to the next page where we have some more examples. So the first example is actually an accumulation problem. These are the types that we have already encountered before. It's just a review. So water is being pumped out of a holding tank at a particular rate in liters per minute, where T is in minutes since the pump started. If the holding tank contains 300 liters of water, when the pump started, how much water does it hold 20 minutes later? A couple of things we need to pay attention to on this problem. First of all, is we're starting out with 300 liters. Now we've done this kind of problem two different ways. We've done the integral equals f of b minus f of a, and we've put that, the 300 over there. We've also worked it to where we're starting, and I'm going to work it the second way because we're not as comfortable, or maybe we just haven't done enough like this. So I'm starting with 300 liters. I'm going to take out the part that's being pumped out. Okay, I'm going to take that out. Now, the rate that they give us, that equation, we don't know whether that's going to generate a positive number or negative number, because they could write that equation either way, so we just need to pay attention. And just pay attention. It is written in minutes, and we're asked in minutes, but it just as easily could have been written in hours, and we could have been asked in minutes. So we need to pay attention to our units. Right, since it's written in minutes and they're giving us minutes, we're going to go from 0 to 20. Right, that's what our bounds would be. 0, where's the beginning of time, to 20 minutes. If this equation had been written in hours, would I still use the number 20 as my upper bound? No. Right, I'd have to convert that to hours, so it'd be 20 over 60, right, or 1/3. So just take, be aware of your units. So we're going to take out the integral from 0 to 20 of the rate that the water is being pumped out of the tank. So now it's a matter of putting it in our calculator and calculating that. And we get 250.309 liters. Now here's where we would be able to tell whether that equation was written as a positive or negative number. If I subtracted that rate, the integral of that rate out, and had gotten a number bigger than I started with, what would I have to do? Instead of subtracting here, I would have to add, right? We just need to pay attention, because it depends on how the equation is written as to whether it's going to come out positive or negative. We just need to pay attention to make sure it makes sense. All right, so that would be a reminder about our accumulation problems. Okay, the next problem, we're looking at a city can be approximated by a circle of radius 8 miles. Okay, it's a circle. So we're talking about population on a ring. Let's see. Moving away from the center of the city along a radius, the population density can be approximated by, and then we have this function right here that approximates the density and people per square mile. Find the population of the city. Okay. So this is kind of just a general picture of a ring. We're looking at that scenario that I showed you, that if we were to slice the ring and open it up, this side would be 2 pi r, it'd be the circumference, right? And that would be delta r. So what we're going to have to do in our integral is we're going to have to integrate, we're going to have to do the density function, which is the 2000 e to the negative 0.15 r, and we're going to have to multiply that by, is it negative? Multiply that by 2 pi r dr. So I have the density function times this width, if you will, or length, however you want to term it. So let's talk about what our bounds would be. Now I'd like you to think we are in terms of r. R's radius. We don't deal with negative radiuses, right? We don't. So this formula is based on the radius, and the smallest the radius can be is 0, right? 0, there could be no radius. So we start at a radius of 0. And they want the entire population of the city. So we have to go all the way out to the outer edge of the city. And they're saying that the radius is 8 miles. What if they wanted to know about the inner 4 miles? We would do 0 to 4. What if they wanted to know about just a ring of population, say from mile marker for radius 2 to mile marker 5? Then we would do 2 to 5. Okay, so we see how the bounds are generated. We want all of it, so we're going from no radius to full radius. All right, that's what we're doing. So we would put this in our calculator, and we'd get 188,424 people in that city. Okay. All right, the last one is the one on a rectangular. This is population density rectangular. This is the one I was explaining that I didn't have in the original notes that you have, so you might want to copy that one down. So this is just an idea of how we would do over a rectangular location. So we have a city located by a river. Okay, so here's, okay, that's a terrible river. Just go with me here, right? That's a river. And here's our city. Okay, it's right by the river. And it runs for 8 miles along the river, and it's 3 miles wide. Okay. So that is our city. Now, if you think back to our lovely Riemann sums, remember how we make little rectangles? We would need to think about which would be the appropriate way to line up the rectangles. How would we do that? And so for this particular one, what we want to think about is, would population along the shore be similar to each other versus population away from the shore? And I know that that could vary quite a bit. I know that there's no correct right answer, but what we're going to go with is the population closer to the shore would be similarly large or small versus population away from the shore. So we would actually, if we're not told, this would be what we would want to do. So our delta x would be along here, along this side. So could we make a case for it being the other way? Sure. And probably with the problem itself, it would be hopefully give you more clues. This is just a general problem. I'm trying to show you how we set this up with a rectangular area. But there would be more information to where you could make that judgment on which way you're going to do the delta x and which way you're going to do the length. So our formula is we do and here we're just asked to set it up. P of x represents the population density, so we're going to do P of x, and our formula tells us to multiply by the length, which the way that we have it set up is 8. So times 8, and we want the entire population, so we would go from 0 to 3. Or more commonly, it would be written 0 to 3 of 8 p of x dx. Would that change if we were to orient it a different way? Yes, it would change. But for this particular situation, we're going to assume, I know that's a big step, we're going to assume that population along the shore would be more similar. You wouldn't, well, it would just be more similar than population further inland. And so that's why we set them up that way. That's why we set the rectangles up that way. Okay? All right, so that gives us the 3 different types of density types of problems we'll see, and a little bit of review on accumulation. Any questions about that?